Hi everyone, so this is a quick walkthrough on our poster held at the European Conference on Visual Perception, where we establish a parametric framework to generate visual illusions using Python. So visual illusions have been widely studied in the field of vision science as it can help us to understand dynamic processes further upstream in the brain, as well as atypical integration processes affected in different neuropsychiatric disorders. Illusions are perceived because of some manipulation of specific stimulus features. These can be, for example, two equal lines appearing as different lengths, or two equal circles appearing as different sizes, such as in the classic case of the Delbourg illusion. So experiments that use illusion stimuli often manipulate these features to infer certain perceptual mechanisms about their population of interest. However, based on existing findings, it seems like varying these stimulus features doesn't always produce the consistent results that we want. And these replicability issues have undermined the potential of visual illusions in helping us to understand related fields, such as psychopathology. Overall, the field of visual illusion research lacks a dedicated software that is easy to use with systematic steps to generate and report the stimuli so that they can be reproduced and reused by other researchers. Oftentimes, illusory stimuli are manually crafted or obtained via pre-made images, making it difficult for researchers to actually measure the sensitivity of participants to these illusions. Although there are also a lot of illusion stimuli online that are freely available for use, they are not organized in an experimentally ready fashion. So given that there are core parametric properties that are responsible for causing the perceived illusion, the aim of our software, PyIllusion, is to facilitate the creation of experiments where results can be consistently interpreted with respect to the central parametric properties. We also hope that we can increase the convenience for testing a battery of different illusions rather than just investigating one type of illusion, which is commonly seen in previous studies. This is so that both common use illusions and rarely tested ones can be easily incorporated into experiments. Currently, many classic illusions are already available in PyIllusion, but with the open source nature of our package, we hope to continually expand its repertoire of illusions, as long as novel ones and variants of existing illusions are discovered and developed. So we hope to develop PyIllusion according to the evolution of the community's needs. So the core idea of the parametric approach proposed here and implemented in PyIllusion is to dissociate the parameters of an illusion from its rendered output. I will explain using the Ebbinghaus illusion here, which is a common optical illusion in size perception. So as you can see on this slide, the two inner red circles are actually exactly the same size, but the one on the right looks slightly smaller because the outer black circles surrounding it are significantly larger than the ones on the left. Basically, this illusion can be described in terms of two distinct properties. Firstly, the size of the target circles, which are the inner red circles, and secondly, the distractor circles, which are the outer black circles, which directly relate to the strength of the context in causing this perceived illusion. So the target feature can be modulated by the argument difference. This basically refers to the objective size difference of the inner red circles directly related to the target features in which participants are supposed to judge. So oftentimes, participants are usually asked which inner red circle appears larger to you. So for example, here, if we keep illusion strength equals to 0, the outer black circles are exactly the same size, but setting a difference of equals to 1 will cause the inner red circle on the left to look to be actually larger than the one on the right. Secondly, the distractor is modulated by illusion strength, and this manipulates the size of the outer circles relative to the inner red circles. So this basically is the strength of the surrounding context in biasing the perception of unequally sized red circles. So here we keep difference equals to 0, where the inner red circles are actually exactly the same size, but setting an illusion strength equals to 1 will cause the outer black circles on the right to be larger than the ones on the left. So this causes the red circle on the right to look smaller than it actually is. So researchers who are interested in PyIllusion can actually play with different combinations and permutations of these arguments, and this will actually be quite useful for investigating incrementally at which threshold certain populations become susceptible to a certain illusion. Across different illusions, these argument names manipulate different properties. So this can be, for example, length of the distractor and target lines in the point illusion, or angle displacement of lines in the zonal illusion. But the point here is that we keep the arguments constant across these different illusions so that results can be consistently interpreted based on these parametric properties. So we designed PyIllusion this way because in most of visual illusions, the strength of the illusion can be dissociated from the actual difference that we perceive. So allowing researchers to easily manipulate these parameters will open the door for potentially interesting paradigms to be designed. So now I'll move on to a quick code demonstration. PyIllusion is an open source package to generate illusions written in Python 3. And even though it is a programming-based tool, users who are not familiar with Python or other programming languages can easily use it because it requires minimal programming skills. So later on, I'll just show you how users can essentially copy the few necessary lines and tweak the explicitly named parameters. So PyIllusion is already available on PyPy. The instructions to install it are available on our GitHub repository. Basically, once the software is installed, it can be loaded in Python scripts and import PyIllusion. So for those of you who are not familiar with Python or other programming languages, this basically stores the PyIllusion module locally and makes functions accessible by just calling the module name. Right. So, and this is the module name and this is the function name. So the parameters for each illusion can be generated using this illusion name function. So for example, to generate Zollner parameters, you can call PyIllusion.Zollner. To generate Delbert parameters, you can just call PyIllusion.Delbert, so on and so forth. And then we just call the necessary arguments over here. Here we set illusion strength equals to 2 and the difference equals to 0 and save this into an object called Ebbinghaus. So the next step will be basically transforming the parameters that we created into the rendered output. So for now, PyIllusion accommodates rendering stimuli as images as well as psychopy stimuli. But first, I'll show you how it looks like as an image. Before that, we'll just print the parameters to see what has been created. So this can be done with very quickly just by calling get parameters. So here there's a lot of information, but this is a basic Python dictionary. I'll just zoom in on the necessary details. For, as you can see, difference equals to 0 and illusion strength equals to 2 corresponds exactly to what we entered in the arguments over here. And what we do is basically the function Ebbinghaus computes the rest of the necessary parameters so that they can be passed on into the image rendering output later. There's a lot of information here, but don't worry too much about that. You can refer to our documentation as they are all listed and described on what they are. So for example, this refers to the size of the inner left and right circle, and these are the X and Y coordinates of the black outer circles. So this container object basically stores the values of all these parameters and then pass into this rendering function over here. So if you want to generate it as an image, you just call .toImage, and then you can specify the size of the stimuli that you want. For now, this is the default size, which is 600 by 800 pixels. And if I run this line, basically what it does is just it prints the stimuli in my active console. But to save it, you can just very quickly save this into an object called image and then call .save into as whatever name that you want it to be, and then this will be saved into the directory that you're working in. So this will be very useful for novice users. As you can see, the code is very minimal and can be used to pre-generate, and illusion can be just saved as images for passing on into experiments. So I'll just show you one very quick example. For example, my colleagues and I recently built this online experiment based on JSPsych, where PyIllusion images are pre-saved and then shown iteratively. So what I'm doing here is basically just clicking the left or the right arrow key depending on which red circle appears larger to me. So this will continue on for a few trials, but yeah, you get the gist, and the next phase will be different classes of illusions. I'll just stop right here, but whoever who's interested can actually just head on to our GitHub repository to check it out. This is of course still work in progress. And another alternative is to actually render PyIllusion as PsychoPy stimuli. So this is a video of a Python script that we built to set up a quick PsychoPy experiment, and PyIllusion is incorporated inside. So for this, advanced users can actually use this easily by incorporating PyIllusion into their script or their experiment. So what this experiment does is just to generate Ebbinghaus illusions very quickly. This script is also available on our GitHub repository. Yep, so overall, we hope that the parametric framework of PyIllusion will make it easier for researchers to describe, manipulate, and report their stimuli in a concise yet consistent way, which will be critical for reproducibility in illusion research. Ultimately, this will work towards the creation of studies that can investigate how modulating parameters affect behavioral responses and conscious perception, in turn helping us to understand the important commonalities and differences between illusion stimuli and how they are affected across different populations. For more information, you can check out our GitHub repository over here.